All right, so for your lab number 1, just don't forget, it's going to be due at some point. I'm going to remind you when we get a little bit closer to the deadline. But you should really try to take your time, go over the videos, and then let me know if you've got any questions. So for tomorrow, during your scheduled lab session, I will be there. Your TA is still being trained about TLA Plus. They haven't really touched this tool before, but they're learning actively now. So they will be joining us in the scheduled lab session, not this coming Thursday, but next Thursday. But tomorrow, I will still be there. Optional attendance, if you find a need to really talk to me about the labs, about TLA Plus, about PlusCal, or the lecture material, just come by. Otherwise, I might see you in class again, maybe next Tuesday. And also important for you guys to know, also I mentioned this information during the syllabus section. So in addition to the scheduled lab, we also got on-demand TA hours. So Andy is the TA I'm talking about. So he took 4315 with me, also, well, like you guys, about 2 years ago. And he's now working also for us as a software-engineering lab assistant. So I put his email on the e-class. You just go there and then got his email. So this is how it works. Any questions related to labs, you can get in touch with Andy and find his email on the e-class. And he will set up some time with you over Zoom. He doesn't really work on campus, so it has to be virtual. So you guys can Zoom for maybe 10 to 15 minutes in the first instance. Anything that cannot be really resolved, you guys can bring to the attention of me, and I will try to help you specifically. So that's how that works. Yeah, feel free to use these resources. They are really created for you. So if you got any question, any help needed, just go for them. And office hour will just be the same, 3 p.m. to 4 p.m., usual time. All right. Guys, any question about the course in general? All right. That's good. Let's now do some quick recap about what we said last time. All right. Hey, guys, please. All right, thank you. All right, let's now talk about what we talked about last time very quickly, and then we'll continue. All right, so last time we kind of revisited the idea about verification, building the product right, versus validation, building the right products. The only additional thing we talk about is in practice, your implementation may have to rely on some programming library. It's very likely. How can you be sure the library you're using is reliable? And one way to really make sure it's reliable is by doing some exhaustive testing to make sure it really works. You don't necessarily have to verify the entire library. It may not be allowed for your time and resources, right? That's something for your information. All right, we talk about the development process, which will bring all the courses you're taking in your SE degree together, right? And we are actually trying to work on this particular part for 3342 and 4315. We're just trying to make your requirements and design a bit more verifiable in a formal way. That's what we're really trying to show to you. All right, we talk about assurance cases. Again, this is like an optional topic that we wouldn't really cover in any more depth. However, for those of you who might be interested, especially in presenting certification evidences for certifying your system, you can definitely look into assurance cases. They got tons of literature talking about assurance cases. It's just a way to present your evidences in a hierarchical way, like a tree. Right? Also, we went over some very simple example that you can take for information, right? And then we started to talk about comparison between 3342 and 4315. So we talk about the correct by construction approach, like a theorem proving using refinements from 3342. So we talk about having some initial very abstract model all the way to the very concrete model. That's what we did in 3342. Especially we talk about the various proof obligations. And proof obligations are something very specific to the theorem proving approach that we talk about in 3342. In this course, we don't really try to do proofs. Instead, we try to do systematic checks, which we'll get into some small example today. And you guys will actually see how to automatically generate the graph for your system from lab number 1. So also pay attention to it. It's also going to be useful. All right, so that's just revisiting the bridge controller example that you guys learned in 3342. And as I said, if there's any particular detail I think you guys should really recall, I'll let you know explicitly. Otherwise, in the test, we may not focus too much on the bridge controller. But if I have to, I'll let you guys know explicitly. All right, we talk about state space. Is a very important concept. Okay, state space is really a way to measure how complex your system is for verification. The more variables you have, the more complex it will be for verification. Very intuitive. Right, we talk about like just an example here. You can revisit that, but just remember the definition. I think that's more important. And in this course specifically, as you will learn in the various labs, every time you actually want to build your system, you actually have to constrain your system in a way by saying, for example, my variable, rather than just being integer, I may have to say it will only range from certain interval, like from 1 to 10, or maybe 20 to 40, something like that. You need to constrain the state space so that you can build some finite graph for reachability. I'll give you some example today, for sure. That's something we kind of left off from last time. Well, state space, just remember, very important concept. I'm going to keep emphasizing. All right, so that's the example that we started with, a simple counter example, a single variable only. Make it very simple, right? Just a single counter variable that will represent a whole state space. And the safety constraint we have, you can think about it's more like an invariance we want to maintain. That should always be true. So C should be bounded by some minimum value and some maximum value. And also we got some updates, which is going to be unconditional, which is to initialize the system. Let's say maybe 0, which is an initial value. And also, of course, the initial value should be larger than or equal to the minimum value. And wow, the initial value should really satisfy this constraint right away. And also, we got 2 updates over here, or in the 3342 turns, 2 events that may occur in your system. And every event should really have some enabling condition. The event should not be able to happen under any circumstances. There should be some constraint, usually. Okay. So we talk about these 2 constraints, right? So we work out the exact logic here, but that's something you guys did in 3342. So we don't need to worry about for this example. Let's take it for granted. If you want to increment the value for the counter, you want to make sure the value right now is not too big. It must be strictly less than maximum. And also, if you want to do decrement, it cannot be too small either. All right, that's where we started with. And we're going to compare theorem proving versus model checking. We kind of started you halfway about the theorem proving approach. Let's do a recap. And then we'll do a little bit of proof just to brush up a little bit. So it will make more sense to go from there to compare how we're going to do it in this course to achieve the same verification purpose. So that's the sketch we did. We don't need to bother putting this into Rodin, just get an idea. So we got a static part for the system, which will be the context. We also got a dynamic part for the system, which will be the machine. And for the context, we got constants, we got axioms. And for the constant, we just got minimum value and the maximum value. Once they are defined, they're fixed. We don't really change them. And the axioms, which will constrain the minimum value and the maximum value, we have, let's say both of them are natural number. And also minimum is less than or equal to the maximum. All right. And for the dynamic part, which might change as system evolve, we got variable C, the counter, and also we got 2 invariants. If you recall, the convention is, in the theorem proving approach, we assume that we may have to have subsequent refinements into the system. So the model we're having right now is just the initial model. So that's why I call that model 0. We may have model 1, model 2, model 3 later by adding more variables to make it more concrete. But for now, for model 0, we got invariant 1 and invariant 2, just naming convention. So when we generate a proof obligation, we can be more systematic to trace back to which one we are trying to discharge. So the first invariant is the so-called typing constraint. We are trying to define the types for the C over here. It's just a natural number. And also we got invariant number 2. That's so-called a safety constraint. So that should be within certain range, right? Pretty straightforward. And then we got the events. And the when keyword over here, under that, we got some Boolean condition. So this will be the guard. Like under what circumstances should this event be enabled? So it may occur. If C is less than maximum, that means we can keep incrementing until this is not the case. Right? So one thing you can just think to yourself is, I can add it here. Okay. So this one over here, just for this one here. This one tells you when it is not the case that C is less than maximum, that means it is disabled. So the enabling condition and the disabling condition are just opposite to each other. They're logical negation. All right. And then we also got decrement, which will be just the same, right? And also important to really understand every event over here, increment or decrement, they're more like a transition between two states. We talk about the pre-state and the post-states. Pre-state is the state where you start the transition with. And the post-state is the resulting states after applying the action of the events. For example, for the increment here, the effects for the action should be, the value for the counter should be incremented. So you might just go from 0 to 1, you might go from 1 to 2, and 2 to 3, etc. Right? And the idea would be, if we want to prove about, let's say, invariant preservation, we want to make sure in the pre-states, we assume that the invariant is satisfied. And we want to make sure by applying whatever update it is by the events, the transition, the invariant should maintain to be holding. Okay, so that's kind of the proof obligation we want to formulate. Right? And so that's a very important second step. Once you have done your model, you have to formulate a proof obligation and then discharge that. All right? All right. Guys, let's now try that, right? For those of you who thought about how to formulate this condition, that's good. If no, let's do it together. It's been a while. All right? And if you, let's remind ourselves about the sketch of the proof obligation, right? Basically, you have to put all the axioms, and also you have to put all the invariants. And then you have to put the guard of the events. In this case, since we are trying to prove something about the increment events, so you should really put a guard of increments. All right? And all these will be the assumption that we can make on the pre-states. So think about all these over here are the assumption. Oh, you know what? How about this? I'll redraw the diagram, which is very important. Think about this guy here is the pre-states. And then we're going to make some transition over here using the events, increments, INC. And then we're going to have some resulting states. Let me use purple here. And that one there is going to be the post-states. All right. Just watch out the color here. All right, so now let's say after this, we want to make sure informally the post states. Oh, how about this? Let me just say a little bit more better. Since we are trying to say invariant 0, 1, which is this one specifically, C should be somehow bounded by the minimum and the maximum. Right? That's the invariance. We want to say that invariance specifically should be maintained. So here we should say invariance 0, 1 preserved or maintained. Or still holds true in the post states. So this is what we want to formulate is a sequence. This one here. All right, that's what we want to formulate. All right, let's now try to do that. I think maybe one thing I just need, may not dive into too many details about the calculation, but I'll just give you some intuition about how we do it. Let's now formulate this part here. That's pretty easy. Okay. So for this part, for axiom, we got, I'll just put it down here. We got minimum is a natural number. Also, we got the maximum is a natural number. All right, we got the minimum should be less than or equal to the maximum. All right, and then we got, so this part here is an axiom. And also we got invariance. And we got two invariants. The typing constraint is C is a natural number. And also the minimum should be less than or equal to C. And also C should be less than or equal to the maximum. So you can think about the next two over here is the invariants. All the invariants, all of them. And the guard for the events, if you recall, if we go back here, bear with me, this one here, right? That's a guard. C less than maximum. C less than maximum. So this is the guard of the events that we want to verify. We want to prove. The guard of increments. So these are all the antecedents we can have for the sequence. All right. Now, what should we put over here? Right? That's something we kind of learned about how to really put here. Let me put something here first. What we really want to preserve is about the invariant 0, 1. Itself is just minimum less than or equal to C and C less than or equal to maximum, right? That's just the invariant itself. However, we cannot simply just put this guy here over here. We cannot. Because somehow this one here does not really take into account the action that has already occurred using increments. Oh, I really meant to say 2. Thank you. That could be the confusion for you guys, right? Guys, I do apologize. I think I really meant to do number 2. Okay, good. Yeah, that's really more interesting one to prove. Yeah, thank you. Okay, so this one here is number 2. All right, so we cannot, sorry, let me just say it again. We cannot simply just put this guy here directly because this one here is simply just about C. But remember, C is the pre-state value. But C has already been updated using the increment events. And remember, the increment events action is about C plus 1, right? All right, so what we said in 3342 is you want to think about pre-state value and the post-state value. Do you guys remember how to represent a post-state value? What's the notation we used? This is a symbol. Prime. Okay? All right, so just in case you forgot the details, I'll put it here. So C prime and C prime. All right, prime here is very important. That's a post-state value. And we also talk about something called before-after predicate back in 3342, right? So for the increment events, for its action, it has the so-called before-after predicate. And this one here will be very straightforward. This might be the last time I'll refer to this. Okay. So now, if I got C becomes C plus 1, the before-after predicate should be as simple as C prime equals C plus 1. Right? That's a simple case, right? You guys may have seen that before, I'm pretty sure. All right, so the before-after predicate here will be simply C prime equals C plus 1. That's for increment. So what we should do is replace every occurrence of C prime here by C plus 1. And this is indeed the stuff we got to put into the actual goal that we want to prove. Right? So that's the little calculation you will have to do manually. Of course, if you somehow formulate the different axiom, different invariants, the guard action in rodent is going to calculate it automatically for you. There's a way to automate this. But on the paper, you need to know how to calculate it. So the final thing to put over here would be the minimum less than or equal to C plus 1, and also C plus 1 less than or equal to maximum. All right, we are not done yet. We're almost there. We have formulated the proof obligation, which is over here. So this is the sequence that we would like to prove. And I want to give you guys just a little bit idea about what we did back in 3342. Okay, like that. Oh, except if I can just, you know what? Let me make it a little bit better. C prime equals C plus 1. All right, so that's the sequence. So that's about the formulation part. And for the proving part, I just want to go over a few steps with you so you can get a feel. So that'll be enough for us to summarize about the theorem proving approach. All right, let me get one more page here. So what we want to do is we want to prove. Okay, let me copy that once more very quickly. So we got minimum natural number, maximum natural number, minimum less than or equal to maximum. Also C is a natural number, and also minimum less than equal to C, and C less than or equal to maximum, and C less than max. And all the assumption there, and then finally we got this calculated result. Min less than C plus 1, and C plus 1 less than or equal to maximum. All right, so that's the sequence we start with. All right, that's the one. And I want to give you just a few ideas about how to prove it, right? Okay, start with this. So typically, if you want to discharge a sequence, you will find that you got a giant list of hypotheses, which may not be all relevant to your proving purpose. So usually the very first rule we apply will be something called monotonicity, which is to drop some hypotheses that may not be relevant. Okay, so it turns out we only need 3 hypotheses to prove this. I can tell you right away. Okay, you guys can also think about later. It turns out we only need maybe this one here. Oh, sorry. We need this one here. And then we need this one here. And also we need this one here. That's all we need. All right. So now I can do something called monotonicity. And let me do a little bit of this. I can say arithmetic, ARI. Anything that's not exactly in the list of inference rule, but somehow it's kind of a simple arithmetic, I can also say ARI. All right. So here I'm simply going to separate the conjunction. So any conjunctive hypothesis, we know that we can put it into separate lines, basically. I can say this hypothesis is one line, this another hypothesis would just be another line. Okay? So now after this, I can greatly simplify what we have to prove. Okay? And I'll go a few steps further. So I can say, after this, I can say minimum less than or equal to C. And also C less than or equal to max. And also C less than max. That's all I need. And then I got minimum less than or equal to C plus 1. And C plus 1 less than or equal to max. So this is the sequence. And this is very fundamental to the approach we are adopting in 3342. We are saying that in order to prove this original sequence, which comes from the proof obligation, it would be sufficient for us to prove this sequence instead. All right, that's kind of what we said. Yeah, question?
Can we use NL instead of everything?
You mean over here? NL? Yeah, you can use that inference rule. For now, I'm just not recalling the rule. I just ARI. That's just an interpretation we have. Same thing, right? Sure, no problem. Yeah. Yeah. I believe this one here, if for those of you who might be interested, your classmate correctly suggests and L. All right, that's back in 3342. All right. And let's now just do one more step, okay? Whenever you got the conjunctive goal, you got a conjunction here, but it's now to the goal part for the sequence. There is a rule over there called ent_r that will allow you to split a single sequence into 2 separate sequences. I want to show you one more step, okay? And then I'm going to apply monotonicity once more individually so I can show you the shortest one for each one of them, all right? So I can say I want to apply ent_r and also monotonicity at the same time. Okay, so what I would do is I'm going to split this particular left conjunct and also right conjunct, I'm going to prove them separately. That's exactly what this rule can allow me to do. All right. So in order to prove this one, in order to prove this single sequence over here, I will be able to prove two sequences individually. All right. So I'm going to write it down. So I'm just going to write here. Okay. So I'm just going to prove two sequences over here. Okay. The first one will be I want to just use minimum less than or equal to C. That will be the only one that's relevant. That means I'm dropping these two. Okay, for that one there. That one there, I will be able to prove minimum less than or equal to C plus 1. Right? As you can see, this first goal over here is now here. All right? And then what about the second goal? I'm going to put that into a separate sequence. That one there is going to use C less than max. That I want to prove C plus 1 less than or equal to max. So you can think about this one over here is now over here. All right? It's just a separate one. And for this one here, I'm using monotonicity because in order to really keep this one only, I have to drop these two. All right. So this is to say, in order to prove the original sequence over here, representing the proof obligation, it turns out I need to prove this one here and this one here, both of them. All right. And the rest will be, for those of you who are interested, you can go ahead. It should be quite obvious already how to prove it. All right. Dong, da da. Okay, you guys can try. All right, so that's about the approach for theorem proving. Let me recap very quickly, and then I'm going to make just two notes, and then we can move on to model checking. All right, in some ways, it's more like a quick revisit to 3342. So what we did in 3342, in essence, is like as follows. We have to define our model, which will be the static part and also the dynamic part. And then you got to understand about the state transition over here, about each events. And we can formulate various proof obligation, and one of them will be about invariant preservation for each event. Okay, and then we go ahead and formulate, for example, the invariant preservation proof obligation, which is going to use the axiom invariant and the guard for the events we are trying to argue about, and also do a little bit calculation according to the post-states value. Okay, and we're going to use the various inference rules to really help us discharge the sequence. That's basically what we did in 3342. That's the theorem proving. Okay, and two remarks over here. Number one. Remark number one. When the proof obligation, for example, this particular one here is discharged, is proved. In this case, you can easily see that it can be proved. Any combination of the variables or constants will just work no matter what. It's really what you have just proved. Whenever you try to prove something, you really prove for all the possible values as long as they satisfy the types of the variables. In this case, any combinations of minimum and maximum value. You can see in the actual proof over here, we didn't say anything about what exactly is the value for minimum and maximum. We just say they are natural number, and also one should be smaller than or equal to the other one. We didn't say, for example, the minimum here and maximum here could be from 1 to 10. It can be from 100 to 1 million. But those ranges are just included, it's generalized into the proofs that we're doing. That's a very important remark to make about theorem proving. So for theorem proving, you never have to worry about having so many variables or the types are so large. You don't have any state explosion problem like what we're going to encounter in the case of model checking. It's a very important distinction to make right away. Okay, that's remark number one. Remark number two, I also talk about, but I'll just write it down. No concern of state explosion. For example, when the number of values between min and max are so huge, okay? For example, the maximum minus minimum, which tells you all the value that the value can take, for the counter, is huge. All right, this is important for you to see. And the very reason for remark number two is for theorem proving, we never have to really build the reachability graph for model checking. But we will have to when we get to the 4315 approach. Okay. All right, guys, any question about this kind of recap about 3342? Okay, hopefully it kind of rings the bell, right, about what you learned. All right, very good. And after this, let's now talk about the 4315 approach. Okay. Okay, that's good. Okay. And for the 4315, this is actually the word from your course learning outcome. We said it's called an algorithmic approach. Algorithmic in the sense that we have to somehow build the reachability graph and check typically the invariant property as we go. But the good thing is you never have to implement this algorithm in this course. It's already encoded in the tool we're using, the TLA Plus. But you're supposed to somehow understand intuitively how things work. Okay? And the idea is we're going to do some exhaustive search. Okay? In order to be exhaustive, that means we are really dealing with some finites. That means the state space should be usually two criteria. Number one, it should be finite. If it's simply infinite, your algorithm will never terminate, right? It's intuitive. Number two, it should be reasonably small. Otherwise, it would just take too long. We just might run out of memory on the remote labs. Reasonably small. All right, so these two criteria are very, very important to know when you're doing model checking. All right? So we are making the following assumption. So we have this invariant over here, right, which we said earlier, and also we got increment and decrement. And you just got to remember the enabling condition we have, right? So that means increment will be disabled as soon as we reach the maximum value for the counter. And the decrement is going to reach is going to be disabled as soon as we go down to the minimum value. Just remember that, right? It's going to help us on constraining the reachability graph size. Okay? So I'm going to somehow simulate a little bit about how the tool is going to use. But the basic idea will be the tool is going to use some adapted depth-first search to really do this kind of thing, like what you learned in 3101. So algorithmic is primarily depth first. When I say primarily, it's because the tools that may have some specifics that may have already modified the standard depth first search, which you don't need to know. Right? But primarily, in principle, it's about covering every node in the graph that's reachable. Okay, depth first search. All right, let's now try this. Let's say we have some init events. So this is always the initial states. So we're going to start by saying after the initialization, what should be the initial configuration for the state space? So here we assume, let's say the counter value is simply just going to be, let's say, the minimum. Okay, let's say minimum. And minimum here could be, for example, it could be 0, could be some value, right? Just some value. Let's say we start with that. And then for every state, we have to consider all the possible transitions that are enabled. That will be the repeated step we have to apply in order to reach out as far as we can. to reach out as far as we can in each states, in each reachable states. Consider all the transitions or all the events that are enabled. That are enabled. All right, so that's really the principle here. All right, so we want to reach out. That's why it's called reachability graph. And we are saying that for every reachable states. So the initial reachable state we have is just the initial states. We start from there and build as much as we can. Once we cannot reach out any further, we terminate. Okay. Consider all the transitions that are enabled over here. So we're assuming that all the transition we have will be increment and decrement. Init is only executed once and never again. All right, so now for this particular states, for increment and decrement, are they both enabled? Not really, because you cannot really execute decrement, right? Because decrement is going to get a counter value down to a minimum -1. So you should not be enabled. So the only event that's enabled will be increment, right? So you can think about in this particular states, the decrement is disabled, but the increment is enabled. Right? That's very important for you to see when you're building the reachability graph. All right, so what I will do is I'm going to just say I can now do increments over here. All right, and once I do the increments, I will be able to reach a new reachable states. And I got to keep going like this. All right, a new state here. And that one there, accordingly, let's say we start with 0, let's say. That one there is going to be, C will be equal to just 1 after increment. So this is a very important step. So let me recap. From this initial reachable state, we want to reach further. So we got to consider all the transition, all the events over here. Increment is possible. However, decrement is not possible. All right. And let me just make some assumption here very explicitly. Let's say the minimum value is 0 and the maximum value is just 2. So we don't get very big graph, so you can just see the idea. All right. Can we reach any further? Yes, we can. So basically what you got to do is this will be the new reachable state. From there, we can either do increment or decrement. Are they both enabled? Yes. First of all, we can do decrement, which will just bring you back to this states, which is good. Right? So you're going to basically go back here. That one there is going to be decrements, right? You see the idea. And we can also go for increment, which is going to increment the value for counter once more. And that one there is going to give you the value 2. And by the way, the 2 here is really the maximum that we are assuming, right? And this will be the new reachable state. Can we reach further? No, we cannot, right? Because here we cannot really do increments anymore. We already reached the maximum. But we can do decrement just to go back. Okay, is everybody okay about the intuition about building reachability graph? That's basically what TLA plot is trying to do for you. And whenever you say you want to generate the graph for your module, it's basically doing something like this. You can even try to think to yourself, even though we don't require for this course, if I give you a programming task to really build a reachability graph based on some variables, some events, can you do it? It's not difficult, right, if you think about it. Okay? All right, that's only the first half. We only talk about this particular reachability graph. And there another thing, which means we want to make sure this particular constraint for the safety is always satisfied, right? So you can think about conceptually there are two passes that we're doing. Pass number one, we're just building the graph. Pass number two, we're going to start from this initial node and do a depth first search to check for every state and make sure state number one will satisfy this Boolean constraint. And also state number two will also satisfy this, and state number three will also satisfy this. All right? Good. Let me write it down here. So there are really two passes. So you can think about pass number one. You kind of build the graph. Build the graph. And pass number two, check every state. Satisfy the invariance or the safety constraint. Okay. Pass number one and pass number two. In this particular case, we're good because all the values we have, 0, 1, and 2 over here, they all satisfy the invariance. However, maybe there's something I'll demonstrate to you maybe a little bit later in the lecture. In TLA plot, this is even more valuable for you. So I want to just give you some decision diagram for you to consider. So now we're moving more towards what we the mindset for this course. Right? So just remember, we have some reachability graph that will formulate your module in TLA plus. And then we have to somehow check for every state that the relevant safety constraint are really satisfied. Okay? And now let's now think about the possible outcomes. All right? So think about this one here. So what we have is a black box. So we don't really need to know how to implement that. It's kind of a secret to us. So we got a TLA plus model checking engine. Okay, let's talk about the input and output. All right, so this is also conceptually very important for you to know. All right, so the input will be your Pascal module, first of all. So this will be your Pascal module. I'm leaving a little bit details over here, which you will see in lab number one. The Pascal module is not directly checkable. You somehow have to translate it into TLA state machine. If you don't know what I'm talking about, that means you haven't really reached that far in lab number one. Okay, that's something you will have to. All right, just remember what I said here. But it's good for here. Let's say we give the Pascal module to, but another one is the properties we want to check. And the module here, just remember, very important, we got things like a variables, and also we got like a typing constraint, etc. All right. Now we're going to discuss the possible outcomes for model checking machine. You might be thinking, the machine should really tell us either yes or no. Yes, if the property is satisfied. No, if it is not satisfied. Right? Let's talk about yes and no first. It might just tell you yes. This tells you all the states satisfy the invariance properties. This is what you will hope for when you actually try to do things in your programming test, because you will follow similar process. But we will let you practice. I'll give you some example to try it out. Okay? Yes. Also, no. The no is actually a very valuable response from the model checker. All right, let's say, for example, let's say this is somehow my reachability graph. Okay, let's say for somehow I kind of specify the action for increment decrement incorrectly. Let's say, so if I do inits and then I do increments and then I do decrements for this particular trace, init followed by increments and then followed by decrements. somehow I will get to a value that's actually below the minimum, let's say. So this is a particular trace that's going to lead me into troubling states. This is what the model checking can tell me as a feedback. Okay, it's also something in lab number 1 to show to you. All right. So no here tells me there is at least one states. Let me say a little bit more precisely. There's at least one reachable states from the init. At least one reachable states where some invariant property is violated. All right, that's number 1. The tool will simply tell you is actually there's at least one states. That's a very good feedback. And even more, the tool is actually going to give you something called a counterexample or counter trace to prove that if you follow through this particular trace, you're going to go to that troubling states. It's a very good debugging information. A counter trace or counterexample. Is given. So if you follow that particular counter trace, it's going to go to that troubling state. And I'll make sure I demonstrate this to you again, maybe sometime a little bit later, so you can see that. Okay. So we'll talk about the 2 possibility. Okay. But there's another possibility. Guys, any idea?
Is the state unreachable?
Hmm?
Yeah, is it possible that the state is unreachable?
The state, no, actually, you know what? Whenever model checking is working, it will only go for the reachable states. So it's not possible to really go to some unreachable. Unreachable state is simply not check, right?
State explosion?
State explosion, yes. If the state space is way too large, in that case, your model checking is it's not going to be non-responding. It's just going to be busy working, okay? Or you can think about here, the third possibility. The model checking engine is not halting or responding. And as Ferris correctly pointed out, that's exactly what a state explosion problem can cost. All right. These are the 3. And I can tell you guys, don't be too frustrated when you first work with a model checker. You might run into this more often. Because somehow you thought, oh, maybe the way I kind of create my model is quite faithful to the problem description. But somehow not exactly, because somehow you really haven't constrained the state space enough so that the model checker just cannot do it. It's very possible. All right? But if you run into this, it's not too bad. At least you get some feedback from the model checker. All right? This one here, sometimes can be by luck, right? If you're good enough for the first go. Okay. But we'll see. Okay. Alrighty. And I'll give you a little bit of a look ahead. Have you guys heard about a puzzle called Sudoku? Heard about it? Okay, I'll give you a little bit more information. So it turns out by using the model checking engine over here, by tweaking that in a particular way, you will be able to use this to solve a puzzle like Sudoku. And it's going to be put as one of your last lab for you to try. Okay, but I promise once I finish reviewing the practical logic, hopefully today and also next Tuesday, when I start talking about model checking temporal logic from next week or the week after, I will revisit this particular diagram once more. I'll give you guys a little bit idea to think about how to solve a puzzle using a model checker, which you cannot use for a theorem prover like Rodin. It's a very interesting way to use a model checker, right? Anyway, okay, so that's about model checking. And guys, any questions so far? Okay, I think we're pretty much done with the introduction. Let me go through a few more slides. We'll take a short break, and then we can continue with the review. Okay. I know some of your fellow students will have to run for a lab. Is he still here? Oh, yeah, he's still here. Okay, why don't we take attendance right now? Okay, so they're excused just for today because they got to run for another course. Okay. All right, why don't we take a quick attendance? Okay, so before the break, we are pretty much done with all the introduction I want to mention. So let me just see the slide. There might be a few more just to mention. Okay, not here, not yet. Yeah, this slide here is just about 4315. Just remember this paragraph here really talks about the importance of a model. So for you guys' purpose, you want to make sure you understand the definition of a model, which is about an abstraction, and also the importance of a model, right? Even though you guys are not really doing exactly like an architect, but model is really important, like a blueprint, right? And all the points over here about state explosion and also temporal property. You don't need to worry too much about it, but we'll talk about temporal logic. But for now, temporal property simply means it will be something about timing. Okay, we'll get there. For now, we don't need to say too much. So for model checking, there's only a single model, but you got to make sure the state space is, number one, finite, and number two, reasonably small. Okay, so state explosion or combinatorial explosion. Okay, just about combination of the variables. All right, good. All right, so I think this part here is just about TLA plus. I'll just go over some text together with you, right? So we are using a TLA plus toolbox. And also, let me just see here. Okay, I'll also write some comparison in just a moment. So TLA is called temporal logic of actions. Okay, just for your information, the inventor of TLA plus is someone called Leslie Lamport. Have you guys heard about this person before? He is a very prominent researcher who actually received the so-called the Nobel Prize in computer science called Turing Award. You guys heard about maybe Turing machine, right? It's a father of computer science, so Turing Award. So Leslie Lamport, for those of you who might have to use, who had to write some scientific report or mathematical report, there's something called LaTeX. For those of you who heard about it, he also invented that. He's a big figure. Anyway, okay, so that's what we're using. Don't worry, it's not going to be on the exam. I want to mention to you, just a background information, right? Good for you to know. All right, so TLA plus is a high-level language for modeling system, especially concurrent and distributed ones. We're not going to see too many concurrent distributed systems in the labs. There will be at least one lab where you can see. But I want to give you guys more like a logical training about how to use the logical operators and also see how we can use the model checker, as I said, to really solve some puzzle. Right, that's something I want you guys to expose more, but you will see some example. All right, so we want to find design errors. So notice that we are not trying to find implementation errors, design errors, because we talk about design models. Okay, and then it's for modeling software and also hardware, right? Things like that. And then we got an IDE, and also we got some TLC model checker. Okay, and plus Cal. This is the language that you guys have to be familiar with, and this will be the focus, the sole focus for programming test, right? So I know that you guys, programming test number one is coming up before the reading week, right? So I will make sure I will release a PDF guidance about what format you can expect from the programming test at least 1 week beforehand. And also I'll give you guys some example questions you guys can also try, okay? Guys, I'm curious. Do you guys want maybe kind of like a mock-up test? Do you think that might help? Okay, how about this? Why don't we say our plan? We can maybe choose maybe the schedule lab session either 1 week or 2 weeks before your actual test, and then I can set up the lab test mode. You guys can come, optional, come and then do the test. How about that? Okay, you guys can get familiar. Okay, no problem. I'll arrange that. Maybe this will be even better. How about this? Before I actually release the example test back to you, why don't you guys take it first as an actual test and then see how that goes. And I'll give you the test itself and also the solution after the mock-up test. That might be the best way. So you will take the test fresh. All right? Okay, that'll be the way to go. I'll plan for that. All right, that's good. And then, So beyond this lecture, so for your lab number 1, you already see the links about the different resources. Okay, these are the 2 papers I mentioned, but okay. Let me just do one more comparison very quickly, and then we should be ready to go for a little bit logic today, a little bit. We don't have much time, but just a little bit. Okay, so I want to compare once more about the tool. So in 3342, so you guys got a rodent tool. Rodent, and then that one there is really for refinement. You can define several machines, and one machine can be declared as a refinement for the other. Okay? So it's more like a refinement tool. And in 4315, the current course, so what we got is a TLA plus toolbox. And important to notice, there's no notion about refinement. No notion. Once you declare one module there, you cannot say it's declared to be the refinement of another module. You cannot do that. All right? There's no notion of refinements. All right, now let's talk about general structure, just to be clear. Otherwise, you might be confused. So in the case of rodent, just for your information, you might say, I got one machine, the dynamic part. I might just call the M0. And then maybe I got variables, maybe N. So this could be one machine, right? Of course, you also got events, invariants, etc. And then you might just declare another machine over here and maybe call M1. The naming convention go from 0, 1, 2, 3. 0 is the initial one, the most abstract one. Machine, maybe M1. And then you also got different variables. You got A, B, and C. Yeah, for this one, just to make it a little bit clear, it's M1. And you may declare that one machine is the refinement of the other. You can say it refines. And you don't need to worry about refinement for this course. Okay? For this course, what you got to worry about will be you got individual, separate, independent modules. So you might just get individual module here. Maybe you got M0 for module. And also N. And also you got another separate module, which has nothing to do with other modules. A, B, C. And if you want to reuse the N, you can also put N here. All right? Oh, I forgot to mention. If you declare, let's say, M1 refines M0, you also got access to N. It's a little bit like an inheritance. But if you got independent modules, if you also want to make use of N, you got to declare that as well, because they're independent, right? And each one of them got their own properties you have to check separately. Right? Of course, you got to watch out for state explosion, always. Okay? Your number one concern for this course when you do model checking is state explosion, which is about how complex the variable types are. Okay? All right, that's good. That's good enough for comparison. All right, let's do a little bit review of the logic. All right, the slides is already on the web. In 3342, I also used similar slides to really talk about proposition predicate. But for many of you, since it's been a while, so I'm just going to talk about similar stuff once more. I think it's going to be beneficial when you learn about temporal logic as well, because somehow temporal logic builds on top of predicate logic. So I think we definitely should really make sure you're comfortable with it. And for the sets, relation, partial function, injective function, we don't really need that per se. But there will be maybe one or two occasions where you have to use things like a power set, partial function. Maybe when we get there, I'll give you a little bit quick brush up. I think that might just be enough. We don't need to spend like 40 minutes reviewing power set, sets, etc. We don't need to. Okay? So for this lecture here, we're just going to focus more on just predicate logic and proposition logic. And I will be I'll also give you guys some reminder about syntax you got to watch out for your programming test. Okay. All right. Today we'll do something very simple. Okay. Okay, we're going to review proposition logic. Most likely that will be what we can cover today. Okay, and then practical logic, especially you can think about practical logic like an extension to propositional logic, where we can use universal versus existential quantification. Okay, we'll get there most likely on Tuesday. And let's say proposition logic. Let's go some slides, and then I think we can just finish one thing today. Okay, a proposition, very simple, just true or false. You don't have any notion about some range of the variable. This is something that we have called universe of disclosure, which is only applicable when we talk about predicate, which I'll emphasize once more when we talk about it on Tuesday. But for proposition, it's either true or false, not both. Okay, either true or false. Boolean, and then true or false. And we got different operators. Very straightforward. You got negation, truth table. You got conjunction, disjunction, implication, etc. Right? And I will talk more about implication next time. And there are different ways to describe implication. Could be a little bit tricky, but we need to go through it. And also, if and only if. We can also formulate it a little bit. But for today, I just want to say a little bit about conjunction and disjunction and draw a little bit connection to Java, which is a programming language you guys are familiar with. You may have heard about this kind of discussion back in 3342, but I think may not be bad to brush up quickly. Okay? I think it's a very important notion for you guys to know what distinction there should be between programming and also logic. Okay, that's a truth table for you. We're gonna dive very deep into this particular column here about implication next time. Okay, I'll get there next time. But for today, let's talk a little bit about conjunction, disjunction. Okay, let's now talk about it. That'll be it for today. Okay, hopefully 10 minutes will do. All right, so here, very easy. So you got P and Q. Because P can be true or false, Q can be true or false. We got 4 possible combinations between P and Q. Straightforward. And one thing to note, in order for conjunction to be true, the only way to make it true is when both P and Q are true. Otherwise, just false. All right? Symmetrically, the only way to make the disjunction false is when both operands are false. Otherwise, if any one of them is actually true, it will be true. Very important insight, which I'm pretty sure you know. All right? So now, this is a very important question here. Okay? Are the logical conjunction and disjunction operators equivalent to the programming and or operators in a language like Java, Python, or C#? Are they equivalent? Are they work the same way under all circumstances? Well, most likely, if I ask you this question, it must be no, right? Otherwise, why should I bother asking you? Right? But how exactly are they different? Adrian?
Java's operators are short-circuited, which means something isn't evaluated.
Yeah, exactly. Short-circuit evaluation is definitely the key over here. Okay. So I want to remind you guys something. Okay, I'm going to present it in a slightly different angle, which is equivalent. Okay. So you guys heard about in 1090 something called commutativity. Okay. In logic, when you say the operators commute, it simply means if I say P and Q, Q and P, they are equivalent. Commute. Doesn't matter the order. Also, if I say P or Q, Q or P, they are also equivalent. That's logic. However, in Java, in programming world, the logical, even though they call logical operators, but they do not commute because we have to somehow satisfy what's going to happen at the runtime for evaluation. Okay, so I'm going to write it down. Okay, there's a little exercise I will do, maybe not today. We don't have enough time, but let me mention definition. We'll do the exercise next time altogether. Okay. Commutativity is only for math. But what about for programming? All right, for programming, if I say P and Q, assuming that P and Q are simply Boolean variables, let's assume, okay? Versus if I say Q and P, they do not work the same way. They are not necessarily behaving the same way at the runtime. That's important, right? I'll just say they are not really equivalent. They don't mean the same thing. How about that? All right? Also, if I got P or Q, Q or P, they are also not equivalent in general. Okay, let me talk a little bit more about this part here. Okay, as for programming, let me elaborate a little bit more here. All right, so here, for short circuit evaluation, basically I'm just going to quote you the facts. When I do P and Q, how about this? I'll mention the facts over here. I should have enough time to talk about one small example. Okay, over here, for this one here, there are two cases at the runtime. Oh, first of all, evaluation is going to be from left to right. Evaluation is from left to right. Okay, case number one. P evaluates to true. If I know that P is already true, according to the truth table, if Q happened to be true, the result will be true. But if Q happened to be false, it will be false. So I really need to evaluate Q as well in order to determine, right? P evaluated true, that means we still need to evaluate Q to determine. That's case number one. Case number two, if P evaluate to false, according to the truth table, you can see that if P is already false, it doesn't really matter what Q is. It will just be false anyway. So we don't need to evaluate Q for efficiency reason. All right? Skip the evaluation of Q, and the overall result is simply just false. That's the exact definition for short circuit evaluation for AND. All right? In order to define the short circuit evaluation for OR, it will be symmetric. So let me be a little bit lazy here. So when we talk about P or Q, right? I'll put purple, P or Q. Okay? The evaluation will still be from left to right. That one is the same. We've got to evaluate P and evaluate Q. All right? So now in the case of OR, if P evaluate to false, for example, right? If you look at P or Q, if I got false over here, if Q happened to be true, P or Q would be true. If Q happened to be false, it would be false. So I still have to evaluate it, right? So still need to evaluate Q. On the other hand, if P evaluate to true, if you look at the truth table, if this is true, doesn't matter what this is, it will just be true anyway. Okay? Skip the evaluation of Q, and the overall result will just be true. Okay? Hopefully you can see what I'm doing here. Just a little bit saving some writing. Okay, I'll give you guys some exercise to think about, and that'll be the starting point for next time. Okay, I'll put it down here. Give me one moment. I want to be more consistent with my notes. Just bear with me. There we go. So I want you to consider two things. So one would be I less than a dot length, and AI larger than or equal to 10 and I larger than or equal to 0. All right, so that'll be number 1. Number 2, I larger than or equal to 0 and AI larger than or equal to 10 and I less than A dot length. Right, for you to think about, and we'll give you the solution and discussion on Tuesday. So here are 2 things I want you to think about. Question number 1. Does it work for each one of them? Does it work at the runtime always? If yes, show it. If no, give me a counter scenario where things will fail. Where failure or exception occur. All right, so think about it, and then we'll continue from here. Thank you so much. I'll see you on Tuesday, but I will be in the lab session tomorrow. Okay.